Hi everybody. So today I'm going to be comparing my custom built autoencoder to an autoencoder from PyTorch. So let's get right to it. So there are certain things that I forgot to do in this. I need to declare the bias layers. So I will come over here and I'll call this self.b1 equals empty dictionary. And then this will be self.b2 equals empty dictionary. So when it's being initialized, this is going to be self.b1 of u equals -1.0. And over here, it's going to be self.b2 of u equals -1.0. So now that we have that, I'm going to come back here to the training, and I'm going to do plus self.b1 of I, and this also plus self.b1 of I. And then over here, plus b2 of j, almost caught myself, plus b2 of j, self. Yeah, self b2. Okay, so now what I'm going to do is I'm going to backpropagate the beta, so that is going to be, let's see, I feel like beta of I, so self dot beta 1 of I plus equals the sum of error. And then over here, it'll be self.beta 2 of j equals the sum of error. No, plus equals the sum of error. So let me go ahead and run this code. So it's going to be Python 3 anomaly.py. Okay, so there's a lot of training going on in this. Okay, aside from that, let me do this. I'm gonna take out plot all this. I'll just make this be equal to c equals the length of x1, and let me define x1 as 0.23, 0.66, 0.45, 0.023, 0.15, 0.98. Okay, so there's 6 values. So I'm going to build this, and then I'm going to do AI of x1, pass it directly through here, and then I'm going to run it. So let me go ahead and save this, and then do clear python 3 anomaly.py. Okay, so it ran through. Now I would like the anomaly score, so I'm going to come over here and do self.anomaly equals empty list. And then I will also refresh it here. Refresh it as an empty list, and then come down, I think right over here. This will be self.anomaly of the sum of error. Self.anomaly.append. Almost forgot that important step. So now I'm going to come down here and do for anom. So I'll call this, let me go ahead and create this as anom equals empty list. For anomaly in ai.anomaly, this will be anom.append anomaly, and then I will do ax.cla, ax.set title of AutoEncoder anomaly, and then this will be ax.plot anom color equals red, and ax.set x label to epox, ax.set y label to anomaly, and then plt.pause 0.1 and plt.show. So I'm going to run it. Okay, so there seems to be a mistake in this. The anomaly is generally supposed to go down in conjunction with the learning rate. I mean, no, in conjunction with the epochs. So if epochs increase, anomaly should decrease. Um, Seems to be leveling off though. I know exactly why that happened. Let me come back here to where I'm optimizing beta. So instead of it being plus equals, it should be minus equals. So B1 minus equals the sum of error. So let me go ahead and refresh that. Okay, now it's perfect. So now it's dropping in an anomaly. Okay, so I believe that's good enough. So now let's bring in the PyTorch. So let's see. So I'm going to come up here and separate that and do import torch, import torch.nn as nn, and import torch.optim as optim. So what I want to do with this now is declare it as def of PyAutoEncoder. So it takes the input size and epochs equals to 200. So this will be, so wait, how far do I do this down to? I do it down to 3. So yeah, there will be 3. So this will be class neural network inherits module. I know a class within a function, that sounds crazy, but I do it. And then initialize it. So it takes no arguments. But this is going to be super of neural network self dot init, and then this is going to be nn, so self dot encoder equals nn dot sequential, and it's going to be nn dot linear of input size to input size minus 1, nn dot sigmoid, and then nn dot linear of input size minus 1 to input size minus 2, nn dot sigmoid. Oh wait, I forgot the comma on these. Not good. Okay, so then comma here. So let's see. This starts off at 6, so 6554. So yeah, this one's going to be the cutoff. Nn dot linear of input size minus 2 to input size minus 3, and then nn.sigmoid. Did I put the comma? No, I didn't. Okay, so 655443. Okay, perfect. So I will now forward propagate it. So forward self x. So it's going to return self.encoder of x. So now I will come over here in the function and declare model equals neural network. Doesn't take any arguments. So this is going to be, so actually I have to do it this way. I have to input x as a variable, and then over here I can do input size equals the length of x. So the neural net will be able to get it, and then this is going to be criterion equals neural network dot mean squared error loss, and then optimizer equals optim dot atom, and it's going to be model dot parameters, and learning rate equals learning rate. So that's something I need to incorporate here as well. So learning rate equals 0.1. I also need to input that into here as well. So it's going to be learning rate equals 0.1. So this will be self.lr equals lr. And if I come down here to the gradient optimization, this is going to be so the gradient of self.lr times gradient 1. This is going to be self.lr times gradient 2. I think I have to do it for the biases as well, so self.lr times the sum, self.lr times the sum. So now that I have all of that, I can come here and do for epoch in range epochs. Yeah, let me just make sure it's in line. So this will be out equals, well, actually, maybe I should do it this way. I should automatically convert it to a tensor. So this will be torch.tensor of x, and data type equals torch.float32. So that'll go through them. So out is going to be model of x. And then loss is going to be criterion of out by x. And then optimizer dot zero gradient loss dot backward optimizer dot step. And then I'm going to print epochs left. So this is going to be epochs minus epoch. And then I'm going to create a variable here called anomaly and do the same thing. So anomaly dot append loss dot item. Oh yeah, it has to be square rooted. So the square root of the loss dot item, and then I'm going to come here and return anomaly. So all I have to do is call PyAutoEncoder. So let me go ahead and I don't need this code like play game from the last one. We're just going to visualize the training. So I got x1 right here. I pass it in. I also need to do it for PyAutoEncoder. So I will call this PyAnomaly equals PyAutoEncoder of x1. So this is going to be p-anomaly in zip AI anomaly to PyAnomaly. I'll call it pnom. So this is going to be pnom.append PyAnomaly. So I'll call them autoencoder anomalies, and then label equals homebrew, and ax.plot pnom, color equals blue, label equals PyTorch. So now we're going to see these in action. So run it. Okay, oh, so there is a dimensionality issue with this, the way that I coded the autoencoder. Yeah, I did it wrong. So let me come back here and call this decoder. And you know what? I'm just gonna hard code these in. So 3, 4, 4, 5, 5, and 6. Okay, so clear that and then run it. Okay, there's still an error. Size of tensor 3 must be. Hold on. Oh, right, because I had to do self dot decoder here as well. My mistake. So reset this. Run it. Okay, that's weird. Okay, so I think I know what the error is. Let me go ahead and print loss.item. So now I will open the terminal again, run it. Okay, I think so the mistake that I made was I should have just done loss item, not with the square root. Um, because that proved to be a singular point. If I come down here, so unnum and pnum, plot pnum, um, okay, there's some sort of thing affecting this. Hold on, let me run it again. I'm trying to figure out why the PyTorch one has like so many different versions of this. Um, yeah, let me debug this code. So the my autoencoder is fine. So neural network model neural network. Okay, so pi anomaly. Okay, let me go ahead and print these out. So, oh, that's where the error was. Let me come back here. P anomaly was not inputted, so this is going to be pi anomaly. So now let me go ahead and run it. Okay, so we can see that my autoencoder has a higher anomaly rate for the same data as PyTorch has. Um, it's most likely because PyTorch is much more optimized than mine is, so it's able to. Well, then again, if the anomaly is higher for something, that means there's more information to be extracted from them. So it kind of seems like the higher the anomaly, the more less regular the data is. So this actually makes sense the way that I trained these. Let me do this. Let's see. So I have learning rate as an input. If I were to do like if I come over here and do learning rate equals 0.001 and then assign it here, so LR equals LR, and then over in PyAutoEncoder do the same thing, LR equals LR. I'm gonna go ahead and run it right now. Shit, is my battery almost dead? 18%. Okay. Yeah, they're so spread apart. But I guess it is what it is. Like it's just how it works. PyTorch is more sophisticated. But if we actually, now that we know, let's take a look at their actual curvature. So what I'm going to do here is, before I close the video, I'm going to do 1, 2, 1, and ay equals fig.add subplot 1, 2, 2. So I'm going to visualize these in separate charts. So it's going to be axay.cla, ax, so ax title is my AutoEncoder, ay.set title is PyTorch AutoEncoder. So AX, AY, set X label. Also AX dot. No, I don't need the legend. So now run it. Okay, so they're both dropping linearly. They both look the same, except it's just the level of anomaly between them. So that, yeah, so it pretty much just boils down to neural network architecture. But it seems like the PyTorch one is sort of curving. Yeah, let's just ride this whole thing out. While my autoencoder is going in a linear formation. Most likely due to the way I programmed it. Um, but yeah, it reached the 200 bucks. So yeah, I thank you all for watching this video. I'm going to keep coming out with more and more good machine learning content, so stay tuned. Peace out.